Hello, today we're going to be working on problem 4.36 with material from the first test. In this problem specifically, we're going to be working with resistors, voltage, and power. And one of the main concepts I've been working on is conservation of power. Essentially what this means is that whatever power is created has to equal the power that is absorbed within the circuit, right? This is actually a law, right? Conservation of energy, conservation of power. Therefore, whatever is created within this circuit here has to be absorbed by itself, essentially, right? So the way they want us to solve this specific problem is actually the mesh current method, which in my opinion is my favorite method. Essentially what it is going to be, we're going to choose meshes basically to solve for the current, and once we have the current, we're going to solve for power, because power, the equation for power is actually P is equal to V times I, correct? And then power can also be solved with P is equal to I squared times the resistance. Problem. Let me change color really quickly. Something rather easy to see. Alright, so the way I like to do my meshes clockwise, right? So I'm going to set this one as a mesh, and I'm going to make this one I1. So that's going to be my first current. Then I'm going to make this one my second mesh, I2, and then my very last one, I3, right? Alright, so once we have that, we're going to start solving for the currents. So let's see, 1 second. We'll go with this one, it's fine. Okay, so this is how I like to solve it. I name my meshes so I know which one I'm working with at all times. So I know this one's mesh 1, meaning I'm working with this one right here, right? So I'm going clockwise. So in this case, my voltage is going to be positive, right? Because the current is entering the positive end. That's how I like to see it, at least. Plus 30 ohms times my current, right? Now, when you, okay, I'm getting ahead of myself. Okay, so then minus 90V, right? Because, actually, my bad. It's plus 90V, because again, the current's entering the positive end, right? So it's positive and positive because it is entering the positive end. Now, this where it gets interesting. Then we're going to go to the 5 ohm resistor. And this one, it's not actually I1. It's I1 minus I3, right? The reason this is because there is current from I1 going through here, it's my bad, I2, right? So there's current going from I1 through this 5 ohm resistor, but it's also current from I2 going against it, right? And because my orientation is clockwise, I'm going to make I1 my starting one minus my I2. Then we're going to do the last 10 ohm resistor for this mesh, and same thing, it's going to be I1, except this time it's actually I3, right? Same reason. The I1 goes here, but the I3 goes the opposite end. And this is all going to equal 0. Alright, so now let's do mesh 2. Alright, so for mesh 2, this is going to work like this. So I'm going to start with the voltage right here. So it's 196. My current's entering the positive end, so it's 196 volts positive. Then I'm going through my 2 ohm resistor. So it's going to be I times I2. Now, my current is entering the negative end of the 90V. So for this time around, it's negative 90V, right? Negative. And then same thing, my 5 ohm, except this time my orientation is based on I2. So I'll make my I2 my starting one minus I1, right? And then same thing, my 4 ohm resistor. is going to be I2 minus I3 is equal to 0, right? So now let's do mesh 3. Alright, so for mesh 3, what it's going to be, I'm going to be looking at this top one right here, right? So I'm going to start with my 20 ohm. So my 20 ohm, where this one's just times I3, right? And I'm going to go to my 4 ohm, which is going to be I3 minus I2, plus my 10 ohm, which is going to be I3 minus I1. It's equal to 0. Okay, so that's it. And if you look at everything we're solving, this is what they call, like, just in case there's any confusion, this is KVL, right? We're solving for voltage, essentially. That's what mesh is. And in node analysis is KCL, right? I know at first I had like some confusion into that, but then once, with more practice, it becomes second nature. Alright, so now what we're going to do is we're going to solve for all of our currents. The way I like to solve it, personally, I like doing matrices. Some people will just want to plug in and chug it, but for me, matrices works a lot easier. So the way I solve it, I do like this. I do I1, right? I'm doing my mesh 1 right now, right? I'm going to put like 1 right here. So this is my I1. My I1 is multiplied by 30 ohms plus 5 plus the 10, right? Then I'm going to add my I2. And this one's going to be negative 5 ohms. And then my I3. This one's going to be negative 10 ohms. And now I'm going to add the voltages together, right? So it's 40 plus 90. So it's 130. But I'm going to pass it over to the other side, so it becomes negative 130. Correct? Yeah. Okay. So now we're going to do our second mesh. We're going to solve for our second one. So for our second mesh, I'm going to start again with I1. Keep them in order. That's very important if you're going to do the matrix, the matrix C method. So it's going to be negative 5 ohms, right? Plus I2. It's going to be 2 ohms plus 5 ohms plus 4 ohms plus I3, which is going to be negative 4 ohms, right? And now we're going to pass the voltages over. So it's 196 minus 90, so it's 106. I'm going to pass it over to the other side, negative 106, right? Now we're going to do mesh 3. Alright, so for mesh 3, let's see, it's I1. It's going to be, well, I'm going to keep it as negative 10 ohm. Plus I2, it's going to be negative 4 ohm, right? And then plus I3, 10 ohm, or 20, I'm sorry, plus 4 ohm, plus 10 ohm. There was no voltage on this one, so it's just 0, correct? Alright, so this is how you solve with matrices. I have a TI Inspire, so I don't know about the 84s, but the TI Inspire does it for me. So the way I set it up, it's like this. I'm just gonna keep it like that because I don't know how long, like how much space it's gonna be. Alright, so I'm gonna add it up. So it's 30 plus 5 plus 10, so 45. Right? It's the first one. Then the second one's gonna be negative 5 and negative 10. Then next step is negative 5. 2 plus 5 plus 4, it's 11. And then minus 4. And this one's gonna be negative 10, negative 4. And then 20 plus 4 plus 10 is 34. Right? Okay. So this is multiplied essentially by I1, I2, and I3. And all this is equal to negative 130, negative 106, and 0. My bad, that's a 3. There we go. Alright, so the way you would plug this into your calculator to solve for it, just in case, 1 second. Just in case there's any confusion over that matter, is essentially this. I'm going to name this one A. I'm just going to give you guys the formula, and then X and B, so you guys can like plug it in. So right now it's in this form. When you plug into your calculator, you want to solve for X, right? Because you want to know what the currents are. So you do A, like the inverse of A, times V. Make sure you keep it in this order to get the correct answer. So once you do that, you're going to get a matrix basically, with only your currents, right? So the matrix, the way it's going to give it to you, it's going to give it to you like so. It's going to be I1, I2, I3. Obviously, it's not going to say like I1, I2, I3, but it's going to give you the numerical value. So I have the numerical value right here, so it's going to be -5, -13, and -3, right? So all these numbers go respective with that current. So I1 is equal to -5 amps, I2 is equal to -13 amps, and I3 is equal to -3 amps, right? So the reason it's negative is because actually the current is going the opposite way that I marked, right? The real current, like in the circuit, let me see, let me do it with green. The real current is actually going counterclockwise. Therefore, if you do your meshes counterclockwise, you're gonna get a positive current, but your answer is still correct either way, as long as you know that the current's going the other way. Right. So once you have that, we're not done. The question's asking here, let me scroll back up. I don't know why I scroll back up. So the question's asking for, let's see, use the mesh current method to find the total power developed. Correct. Alright. So the power developed is the power that is being created inside the circuit, correct? So based on what I see right here, what is creating the power? Alright. So the power developed is actually the 40 volts right here. Right? This is creating some power because like the current's coming out of it, right? Because it's going the other way that I marked it. And then also the 90 volts, because again, the current's coming out of it, so that's producing power. The 196 volts is not producing any power, because again, the current's going this way, right? So it's actually coming the other end. Alright? So, yeah, okay, so let's keep on going. So let's calculate it. So I'm going to calculate the power developed for my 40 volts. Okay, sorry. Okay, so the power developed for my 40 volts, it's going to be -40, because my current, or my voltage is facing the wrong way, times -5. Again, if depending on how you did your mesh, this one's going to be positive and then this one's going to be positive. It just really depends on the direction that you calculate your mesh. Either way though, this power should be 200 watts. Correct? Yes. Okay, sorry about that. Alright, so then you keep on calculating, and let's do P90. So looking back, the 90 volts is actually facing the wrong way, right? Because since the current's going this way, right? The dominant is going to be I1 to I2. So the 90 volts is actually absorbing power instead of developing it. Right? I say absorbing, but essentially it's developing and dissipated. Dissipated being absorbing and developing being created. Alright, so the 90 volts is actually going to be right here. It's going to be the 90, right? Notice how like it's the opposite way, right? So it's positive times I2 minus I1, right? So it's the other way. So this is going to be 90 times -130 plus 5, which ends up being -720 watts. Alright? So you have -720 watts, and now we're going to calculate the power at 196 volts. Remember that the only voltage that can be created is from a power source itself, right? It can also absorb voltage, it just depends on which way it's, set up. So now this one's going to be 196 times the current that's going through it, which is negative I2, right? So it's going to be 196, again, the same way it's facing, times 13, which is equal to 2, right? Alright, so based on these power sources that we can see right here, the ones that are being dissipated, or essentially the voltages that are creating power, are going to be P40. My bad. P developed. I just say create and absorb. P developed is going to be P40 and P196 volts. Therefore, when you add them, your total voltage is going to be 2,748 watts, right? So this is your first answer right here to the first part of the question. That's your power developed. Okay, so now let's read the second part of the question. So the second part of the question is like, check your answer by showing that the total power developed equals the total power dissipated. Alright, so remember I told you guys about the conservation of power, right? So that means that the power developed has to equal the power dissipated, right? So how do we calculate power dissipated? Easy. We just have to calculate every other component in the circuit. What does that include? That includes all the resistances and the 90 volts, because we discovered that the 90 volts actually dissipating power, it's absorbing it. So let's start calculating it. Again, we know the current through everything, and we know the formula is, I'm going to write it down again, it's Pi squared times R, right? So let's start calculating. So the P at 10 ohms, this is part B. The P at 10 ohms is going to be I1 minus I3 squared times my 10 ohms. You guys can plug this into your calculator, but this ends up being 40 watts, right? Now, keep on going. So this is my P at 30 ohms, which is going to be I1 squared times 30. This ends up being basically negative 5 squared times 30, which is equal to 750 watts. Okay, so my P at 5 ohms is equal to I1 minus I2 squared times 5, which equals to 320 watts. Okay, now we keep on going because we still have 3 more components to go. P at 4 ohms is equal to I2 minus I3 squared times 4. This ends up being 400 watts. Alright, so now P 2 ohms is equal to I2 squared times 2, which is equal to 338 watts. Okay, so now P at 20 ohms, the last one, is equal to I3 squared times 20, which is equal to 180 watts. Alright, so that's all of our components. So now we have to add them up. So power dissipated or power absorbed is equal to P10 ohms plus P30 plus P5 plus P40 plus P2 ohms plus P20 ohms and P90. Oops. My bad, guys. Alright, so remember, we discovered that P90 was actually dissipating power, right? Because it was negative. These ones are positive just because I set them up that way, but technically they're all supposed to be negative, right? Okay, so now we keep on going. We add them up. 40 plus 750 plus 320 plus 40, or 400, sorry, plus 338 plus 180 plus 720. Alright, so once you add them up, all these in your calculator, you get 2,748 watts. That's the power dissipated, which is equal to the power developed. Therefore, power is conserved within the circuit, and we proved it. We proved that power was conserved by comparing power developed and power dissipated. So we checked our answer. But that also helps a lot in the test when you guys have to do this kind of thing. It helps a lot to check the other end of the spectrum. Alright, thank you for listening, and this is a tutorial for problem 4.36. Thank you.